Well, as the introduction says, I've actually had about 35 years of experience in the nuclear industry now, and I've had the benefit of it being spread across a wide range because I've had fast reactor experience decommissioning on MTRs, as well as a lot of process plant and examination cells. So I've had quite a broad experience. So today I'm going to cover an interesting task, and this is one which demonstrates how a remote in-cell crane was repaired. I should give you a slide, shouldn't I? Yes. My presentation today demonstrates how a remote in-cell crane was repaired in a high radiation environment in a manner which accrued very little dose to the team carrying out the work. And it demonstrates how off-the-wall thinking and teamwork mixed with good use of mock-ups can deliver what others thought was impossible. This particular in-cell 1000 weight crane was operated in long travel by an endless chain that ran the 12-metre length of the cell. It engaged over each crane axle, tensioned locally by an idler sprocket, and over its overall run by an adjustable plumber block at the west end. So this 3D image shows this is the tensioner at the west end. The chain came over there, under there, up over there, and then away off down the cell. The other one here, this is the cable reeling drum, which supplied the cable for the electric power supplies for the unit. The original crane was replaced in 1991 with the current unit, but in 2006 this suffered a catastrophic failure of the long travel chain bearing at the east end. This was repaired but required an adjustment of the overall chain length. The west end adjuster turned out to have seized. This will be no surprise to folk in this sort of industry when you've had something for a long time, and attempts to adjust it resulted in the threaded shaft being sheared and the long travel chain tension was lost completely. It was operated nonetheless, but after a very short period of use the crane crabbed in cell, displaced the chain off one of the axle sprockets, and it no longer had sufficient grip to return to the maintenance box. So it was assisted in with the main power cable. This caused damage to the cores of the supply cable, and all functions were lost by this stage: lifting, cross travel and long travel. So I don't think we can really call it a crane anymore. Now, here we see the maintenance glove box during the original construction. Wrong button. Oh, what am I doing? Apologies, I'm not very good with this machine. This is the thing in its construction state, so before it's encased and all this wonderful stuff. So this is the maintenance glove box during original construction, and as it now was, with lead shielding encasing it to reduce the radiation dose in the ambient area. The dose rates in the glove box were by this period in the cell's life generally about 350 millisieverts per hour gamma with a significant additional beta dose, so repair was not going to be simple. As a consequence, the crane actually sat in there for 6 years and the cell generally degraded due to the loss of what is a critical service. This included the failure of a zinc bromide window in 2009, which could not be replaced due to the crane non-availability. As a consequence of this and a number of other issues, I was assigned to look after the facility and address the many problems that had developed. My first approach with the crane was to look at the options of repair or replacement. To save time while reviewing the options, I commissioned the construction of a new crane to the existing specification, which would give me a full replacement, or one from which I could obtain as many parts as I needed. To repair the existing crane would involve man entry to the maintenance glove box to replace the drive motors, for which there was no available lifting strategy, because actually there was a door there which you could take the lead away and get to, but even once you got into it, there was no means of handling these things. Now, these lift motors were actually very heavy, so you'd have to get someone in an airline suit in a heavy dose, and you'd have to try and work in. So actually it was not what you would call a very good job in today's environment. So this was going to incur significant dose due to the shine path from the main cell, where dose rates were up to 10 sieverts an hour. In addition, replacement of the supply cable was going to be challenging due to the high surface beta dose associated with cutting, replacing and reconnecting it, caused from its many traverses up and down the cell. When collective dose rates were considered, no satisfactory methodology could be determined, which explains why it sat for the number of years it has sat. So I have a degree of sympathy on that point. There was a shield door installed between the cave and the box to reduce shine, and that was in there. But the drive screws which operated it had failed on the one previous time it had been used, and that had required about a year to recover that problem. So there was concern also that the door itself was by now heavily contaminated, and that may result in as big a dose down as up, and therefore repair by the installed method was not looking feasible. The other option which we looked at that point was replacement of the whole crane through the roof of the containment. Because there's a scope there, we could have cleared that, lifted the old one out and put the new one in. But that would still have required cable work as well. But this too proved challenging also from the radiological, because the shine path coming up from the cave was beaming up this way. And of course we would need to build a working platform up here, and even the dose rates in the vicinity to build the working platform would be significant. So although we had space to work, there was no really ready access to do that. Now, by this time, a bit of progress, the replacement crane had been manufactured, tested and delivered to site. To assist with the process of optioneering, a mock-up of the whole maintenance glove box was manufactured to test out the ideas. Now here we see the assembly during final construction in the off-site workshop. Working through the options on the mock-up, quickly identified that neither repair or replacement in the glove box was practicable due to the radiation dose the operators would receive. So at this point, we'd confirmed what we suspected. But all is not lost, because a mock-up's a great machine. Now this meant that a radically different approach was going to be required, repairing the crane remotely within the protection of the bulk cell shielding. Now, not the first place you would think about, because it's up above the manipulator level, so it's not very good to get to. And this is also a plutonium cell, and as such has very few penetrations, so there's not much to go on. But look to see what we've got. So a review of the cell identified there was only one penetration potentially of use, and this was the redundant laser through tube which projected vertically down from the roof of the cell. Now this effectively is like a scaffold tube really. It's 1 5/8 inch diameter, so it's roughly like having a scaffold tube. So the mock-up was extended to include the first stage of the main cell where the penetration was installed to see what could be achieved. Now, before any work could be carried out in cell, the crane would actually have to get there, because at the moment it's in the maintenance box. And this would require a repair to the long travel tensioner, and then the refitting of the chain onto the sprocket first. Even the internals of this extension box were sufficiently contaminated and affected by the shine paths that direct entry by removal of the shielding was not looking attractive. Because bear in mind, this is a mock-up of it. This is all surrounded by lead shielding. To take that away to gain access to this was actually going to be reasonably dosy in itself. So we got a mock-up of the tension cabinet, and a novel approach was developed to recovering the sheared rod. So the main principle adopted was of using the installed shielding to protect the workforce, which is something I tend to do quite a lot. Where you've got installed shielding now, I use that as my primary design safety principle really. So here we see our mock-up. We replicated the lead shielding and we did a bit of coring. So what we did was left the shielding in situ and created small penetrations as necessary. A core was taken of the lead shielding and then a threaded collet assembly manufactured to attach to the shaft. Now we trialled this and it actually worked very well. So here you can see where we made up a threaded collet that would slide on and then latch onto the thread of the sheared assembly. So we trialled this nicely here and found that this part was going to work. So we did a safety justification for this element of the work, which was simplified by the mock-up demonstrations, which proved the technique, allowed good time assessments for calculation and so on. And the area was then tented out as the glove box integrity behind the shielding was suspect given the number of years that it had been lying, and the lead shielding was cored. Now, I tend to jump back and forth with quite a lot of mock-up pictures, more because it's easy to see. So you've got a combination here. This is a mock-up here, and this is the real thing here, because it's easier to see on the mock-up how the arrangement was. There's the threaded shaft there, and that's where we pick it up there, and that's the main drive chain going off there. Now here we see how the assembly actually looked after and this is how it looked after we cored the lead, and that is the end of a broken piece. So there's a broken piece comes back to there. So one of the tricks we had to do was get that out remotely, because again we're looking down through the lead shielding. However, all was not lost. The new adjuster worked very well. So the next element of this piece of work was to reattach the chain. And this is where, again, great plans. The original plan was to remove a lead plug on the side of the glove box shielding, because this should access a glove port close to the sprocket. However, once we got the plug open, we found it didn't line up at all. So the drawings were a little bit awry. Now, using the mock-up, we experimented with long-reach tooling, and using through-the-cord penetration. So we actually used long-reach tooling coming in from here, up there, right to get to here, because that was how the thing was sitting in reality. This is the mock-up, but that's how she was sitting on the real thing. So we were looking at about 4 or 5 feet there at a distance, just to get some kind of perspective on it. And this is where we found a mechanical craftsman proved very adept at refitting this blind, because I had a shot myself, and yes, it was quite easy, or not too bad when you could see, but of course this was all encased in lead. So this had to be done completely blind, and the best we had was poking a camera up through the hole there, trying to see there. So a mechanical craftsman, they turned out to be very good at doing this. So using a CV reacher, with one little deft flick, the chain was on. So that was phase 1 now complete, and the crane could now be moved out into the cell for phase 2. Now, there were 3 elements to the remaining work. The cross travel had to be addressed, the lifting capacity had to be addressed, and also the power supply requirements had to be addressed. Now, my first approach on this was to see if I could get rid of electrical power completely, because no disrespect to any electrical people in the audience, but I find electrics are the bane of my life. So, and especially so in remote high radiation environments. Now, for the cross travel I succeeded, because it didn't really need a powered motor there for what is just an in-cell cross travel. And by removing this unit and fitting on an equivalent one but with a manual chain on it, it was actually quite easy to get one that the manipulators would be able to just drive it back and forth. So a manual chain wheel drive system was designed, which would replace this, and that was actually, so replacing the cross travel was there for the next challenge. Now, these units are held in here, you'll see, by a bolt, and there's a couple of pins. So working through our scaffold tube, using long reach tooling, we managed to unscrew the bolt, nice bit of careful work, and then using a hook and lifting cord, and then by taking the load of it, and then we actually just gently drove the crane along the cell to get it off the sliding pins. Bingo! So that got the old one off, and basically we got the new one on by the same technique. Now, was it as simple as that? Nearly. The problem we had was, when the original, this is still in the mock-up here, when the motor had been fitted at a previous time, someone had left a bolt, and I can understand why, because when you're working in that sort of environment, you're not hanging about. A bolt had been left just lying, and this fouled the thing coming off. So it actually took us about an hour of careful jiggling and manoeuvring and such like. Fortunately, because we were in a nice shielded environment, having to work for an hour didn't cause us any problem. Had this been a genuine man entry, we'd have been up the creek. So, and there we can show a real shot, just showing looking downwards how we held the equipment to relocate. The equipment was actually posted in via the waste route, because obviously I needed to get these motors and so on into the cell, or its replacement. And so we actually posted that in via waste crates, and then moved it along the cell. That was all right for the lightweight one. For the main hoist motor, which I'll come to in a minute, I had to do something different. So raising and lowering of the units was done with lifting cord and a small winch made up in its own little glove box operated from the cell roof above the penetration. Again, for contamination control, this activity was also carried out in a containment with operators in Tyvek and respirator as additional precaution, because I always like to keep at least 2 barriers for contamination control. So the new cross travel was raised into position, fitting screw operated by long reach tooling from above, and that was now 2 out of 3 functions. So I now had my long travel and my cross travel. So my crane is starting to come back to life. So at this point, I was still challenging, do I need electrical power? Now the snag was the greatest practical mechanical lift capacity I could obtain that was within the operating capacity of the manual manipulators was a 1/4 ton. Now for normal use, I would have been quite happy with this, except that I've got a failed zinc bromide window as well. And there are some temporary shield blocks that would have to get maneuvered into position. And sadly, they were a 1/2 ton. So that meant that moving to electric power for lift capacity was sadly not negotiable. Now the existing electric supply was via the maintenance glove box and a horn and plessy plug arrangement on the back of the crane. But by now, I'm only needing very minimal electrics because all I need is a raise and lower on a hoist. So a new reeling drum assembly was made up to sit just in front of the actual, and that's it there, which will sit in front of the crane maintenance glove box, because one of the great things I've done with this modification is I don't need to go back into the maintenance glove box, because I'm never going to do any maintenance in there because it's too dosy. So in actual fact, the only thing that's coming out of there now is the tail end of the long travel drive. So the crane can now spend its entire life inside the cell. And what I have found is I've now got a technique that's easy to repair the crane. Whereas in the past, if that crane went down, you were looking at 6-month outage. Now it's a matter of days. So that's actually quite a positive. So I could afford to actually effectively block off the entrance to the maintenance glove box with my new power supply, so I don't need to come into it. So that simplified it, because again we could deal with it readily in cell. Now we also changed the plugs into LEMOs because it's a bit more minute friendly, so now we can make and break connections readily with the manipulators. Now another thing about electrics in cell, we tried to get the radiation tolerant cable for this, long lead time, so it's okay, keep the order going, but in the meantime we'll work with lower grade cable. However, actually it didn't last very long before the radiation went for it, so in fact but by that time my other stuff had arrived. So it does demonstrate that electrics in cell are a problem, and you do need to use radiation tolerant cable if you're going to be in for a good while. Now, nearly there. To assist with moving the new electric hoist into position, because the electric hoist is actually quite a heavy thing, so I need a crane to move the crane, as it were. I actually had to go for the mechanical 1/4 ton hoist first, and so the first part was actually to put the mechanical hoist on to give me a 1/4 ton capacity to allow me to then take the electric unit along the cell to where we could do the work. So that's now got the full 1/2 ton capacity. I've always got a fallback of doing a 1/4 ton should I want to derate the lift capacity. So that's always a backup to make it a fully mechanical unit. So External feed for this new power supply was actually fed through a specially prepared plug unit fitted through a manip port. So again, I can now do ready connections and disconnections, replacements without any bother. So that keeps subsequent repair and replacement during decommissioning simple and low cost. So finally, just to sort of sum up, this work successfully reinstated the in-cell lifting capacity, which would allow the replacement of the failed shielding window and then go on to support the decommissioning of the cell. The techniques developed had a number of benefits. Any future repair of the crane is now simple and a quick task, so that the decommissioning program has been de-risked to some extent. The dose uptake to the team on this task was actually very low, and the whole work package accrued a total dose of 700 man microsieverts. The work was also all done in-house by the building team, which demonstrated to them how no problem could be too hard to tackle, and helping them to inspire them to better things, because they had actually sat with this problem not knowing how to sort it. And so this, plus a few other things which we've done, have actually showed them that nothing is too hard to achieve. You just need to have that cunning plan. So the principles adopted to carry out the successful repair were by challenging the existing approach, thinking outside the box, and importantly using a full mock-up to develop trial and practice the techniques. And the final comment I'm making there is actually what I've found out in all my years of work is the safest way of doing these jobs is actually the best way. Very often people think the safe way is more expensive. In actual fact, I would say the safest way is actually the cheapest way. The trick is to find it. There we go.
That's good, thanks. Okay.